Most machine learning courses dive straight into multivariable calculus before showing you how to actually build or deploy anything. Let's change that. Welcome to ML Learning. This series breaks down machine learning concepts through an engineering lens. We'll give introduction to each topic and then provide some questions to check and build the knowledge. Hit subscribe to build your ML knowledge step by step, and let's get started with episode 1 right now. If you are coming from a traditional software or IT background, stepping into machine learning requires a fundamental shift in how you think about solving problems. In traditional software development, the formula is straightforward. You write explicit rules or code, pass in data, and the computer computes the answers. You write conditional statements, like if-else logic, to handle every business case. However, traditional programming struggles when tasks become highly complex or when dealing with massive datasets efficiently. Tasks like natural language understanding, medical diagnosis, or image recognition are nearly impossible to hard code with fixed rules. Machine learning flips this equation on its head. Instead of writing explicit rules, the formula becomes data plus answers, or labels, equals rules, the model. Rather than writing hard-coded logic, machine learning allows computers to learn directly from data, identify underlying mathematical patterns, and make automated decisions or predictions without explicit programming. The end result of this process is a model artifact, which you can deploy much like a traditional executable or microservice. Why has machine learning become so vital across industries? It addresses key challenges that traditional software simply cannot scale to meet. 1. Solving complex business problems. In healthcare, ML assists with image recognition and speech processing to diagnose diseases, personalizing patient treatments. It also powers real-time language translation and sentiment analysis. 2. Processing large data volumes. The internet generates vast amounts of data every day. Machine learning processes this stream quickly to deliver real-time insights, such as detecting fraudulent financial transactions or generating personalized feeds on Facebook and Instagram out of billions of interactions. 3. Automating repetitive tasks. ML automates time-consuming tasks with high accuracy, reducing manual work and errors. Examples include Gmail automatically filtering spam, customer support chatbots handling order tracking and password resets, and automated invoice processing. 4. Personalizing user experiences. Platforms like Netflix suggest movies based on your viewing history, while e-commerce platforms recommend products tailored to your preferences. 5. Continuous self-improvement. Unlike static software, ML models evolve as they receive more data. Voice assistants like Siri and Alexa learn user accents over time, search engines refine query results, and self-driving cars improve their navigation decisions based on millions of miles of driving data. At a high level, the basic data flow of a machine learning system moves from input raw data to interpretation, through an algorithm, into processing, and finally to an output. But how does the machine actually acquire knowledge from this data? It follows an iterative loop. Step 1. Data input. Data is the foundation of machine learning, whether text, images, or numbers. Both high quality and sufficient quantity are critical, because models learn patterns directly from input data. Step 2. Algorithms. Algorithms are mathematical methods that help the system identify patterns in data, such as for classification or regression tasks. Step 3. Model training. During training, the machine continuously adjusts its internal settings to minimize the difference between its predictions and actual outcomes. Step 4. Feedback loop and optimization. The machine compares its output against true target values. Using mathematical techniques like gradient descent, it utilizes this feedback to correct errors and update its settings. Step 5. Experience and iteration. Training repeats across many passes. With more data and iterations, prediction accuracy refines over time. Step 6. Evaluation and generalization. Finally, the trained model is evaluated on new, unseen test data to verify that it generalizes well to real-world scenarios rather than simply memorizing the training dataset. Machine learning is primarily divided into 3 core paradigms: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning algorithms are trained on labeled input-output pairs, where the correct answer is already known. Problem types includes classification, predicting discrete labels, and regression, predicting continuous numerical values. Real-world applications: fraud detection in finance, house price estimation, customer churn prediction, and disease diagnosis. Unsupervised learning operates on raw data without target labels. The algorithm automatically uncovers hidden structures, similarities, or groupings. Problem types includes clustering, grouping similar data, and dimensionality reduction, compressing features. Real-world applications, customer segmentation for marketing, anomaly detection, and pattern discovery in large datasets. Reinforcement learning relies on an agent that learns through trial and error by interacting with an environment. The agent receives rewards for correct decisions and penalties for wrong ones. Problem types, policy optimization, real-world applications, autonomous vehicle navigation, robotics control, and dynamic server resource load balancing. Where do deep learning and large language models, LLMs, fit into this picture? Deep learning is a specialized subset of machine learning that utilizes multi-layered artificial neural networks. Generative AI and LLMs, such as GPT, are advanced deep learning models built on transformer architectures, trained on massive textual datasets to predict text sequences. For IT and engineering teams, deploying machine learning requires more than running an algorithm. It demands an end-to-end operational lifecycle known as MLOps, data ingestion and cleaning. Accounting for nearly 80% of the effort in production systems, raw data is collected, deduplicated, and validated. High data quality is crucial because of the principle, garbage in, garbage out. Feature engineering and selection. Raw data is transformed into numerical matrices through techniques like normalization and one-hot encoding for categorical variables. Model training and evaluation. Data is split into training and test sets. Algorithms minimize a loss function while metrics like accuracy, precision, recall, or RMSE are evaluated against unseen test data to prevent overfitting. Model deployment and serving. The trained model is serialized using formats like Onyx or Pickle and served via REST, gRPC API endpoints or embedded into edge applications. Monitoring and continuous training. Unlike static code, real-world data distribution shifts over time, a phenomenon called data drift or concept drift. MLOps pipelines track latency and feature changes to trigger automatic retraining workflows. To build across this pipeline, the dominant technology stack includes languages. Python is the primary language, C# and C++ are other two languages. Data processing, Pandas, NumPy, and Apache Spark. Classical ML frameworks, scikit-learn, XGBoost, and LightGBM. Deep learning frameworks, PyTorch and TensorFlow. MLOps and managed cloud platforms, MLflow, Kubeflow, AWS SageMaker, Azure ML, and Google Cloud Vertex AI. While machine learning offers automation and efficiency, building production systems introduces significant challenges. Data bias. ML models learn directly from historical data. If the training data contains historical bias, the model will output unfair or discriminatory decisions. Data selection must be carefully audited. Privacy risks. ML relies on vast amounts of data, raising risks around sensitive personal information exposure. Lack of explainability. Complex ML models can operate as black boxes, making it difficult to explain why specific predictions were made, which impacts trust and accountability. Workforce impact. Automation can replace certain routine roles, highlighting the need for workforce retraining and upskilling. To wrap up, machine learning represents a pivot from writing manual conditional rules to building systems that discover mathematical patterns from data. By understanding how data flows from ingestion and feature engineering through to model serving and continuous MLOps monitoring, you can build systems that adapt and improve over time. If you found this breakdown helpful, hit the like button, subscribe for more technical deep dives, and leave a comment below on which ML paradigm you are currently exploring. Now let's check the learning with 25 multiple choice questions on the topic which we covered in this content.